Hello everyone, section 11.4, three-dimensional figures. You got to follow these definitions. You should familiarize yourself with what is a polyhedron and what is not a polyhedron. You should also get to know this formula called Euler's formula, named after Leonhard Euler. Example 1. Tell whether each solid is a polyhedron. If it is, name the polyhedron. So a polyhedron is defined by having polygons for all of the sides, all the faces have to be made up of polygons. These lateral faces are all isosceles triangles. The bottom face here is a pentagon. So this is it is a polyhedron. Yes. And what is it? It is a pentagonal pyramid. Part B, the bottom face is a circle, and the top face, I guess we call it, I don't even know what that's. 9 of them are polygons. This is, well, it's a hemisphere, it's half of a sphere, but it's not a polyhedron. No. Part C, the bases are hexagons, the lateral faces are all rectangles, and this is a polyhedron, yes. It's a prism, and specifically it's a hexagonal prism. Right. Example 2. So we're going to look at these cross sections and see if we can describe what shape they are. So a cross section is formed by taking a solid and taking a plane and cutting through that solid. So if you imagine if there were paint on the plane and it was painting the part of the solid that it touches as it cuts through the solid, you can see how it's this shape is what's being painted out of this hemisphere. So in part A, this painted part, this cross-section part, is half of a circle or a semicircle. Okay. In part B, we have a pentagonal prism, and the plane that is intersecting this prism is parallel to the bases, and it's intersecting and painting and cutting out another pentagon. So if we connect the intersections of the edges, that shape is a pentagon. All right, these solids of revolution and axis of revolutions, this can be a little bit tricky to visualize. This is something that's going to become important for you when you get to calculus. You're going to see these solids of revolutions again, and you're going to spend a lot of time finding their volumes using calculus, using integrations and things called the washer method and the shell method. You'll learn about those when you get to calculus. For now, in example 3, we're going to sketch the solid produced by rotating the figure around the given axis, then identify and describe the solid. So what do I mean by produced by rotating the solid? So here I have a rectangle, and if I take this rectangle and if I rotate it, let's see if I can get it, and I rotate it, it doesn't cut out a rectangle. The shape that's being cut out is circular in shape at the top and at the bottom, but it's a solid, right? Because this rectangle has a height. And imagine if we have a block of wood and it's a drill cutting down into that block of wood, what shape would it cut out of the block of wood? This would cut out a cylinder. If we take this triangle, this right triangle, and we swing it around this line here, this axis of revolution, this point is going to sweep out a circle. And what shape do we end up getting? We're going to get a cone. So that's identifying the shape. Describing the solid is giving the dimensions. So a cone with a height of 6 and a radius of 4. Okay. Part B. Part B is a little harder to draw. What's this semicircle? It's going to sweep out, and what's it going to make? It's going to make a sphere. With, now for a sphere, there's only one dimension to describe, with a radius of 5. Part C. So this is a composite shape. This is a rectangle and a triangle, and they're going to sweep around this line L, and they're going to make a crayon-like shape or a rocket-like shape. And if I try to draw it, I'll try here. So the bottom part here sweeps out a cylinder. This sweeps out a cylinder. And the top, or the right, sweeps out a cone. So if we just identify this shape, this is a cylinder. With a height of 5 and a radius of 3 and a cone with a height of 4 and a radius of 3. Because the cone and the cylinder have the same radius. That's example 3. Example 4. Describe the cross section. So here we have a triangular pyramid. All 4 sides are triangles, equilateral triangles. And we have a plane coming in parallel to this particular base. And if we mark off where it intersects the three edges that it does intersect, and we connect those, and maybe even shade, you see we're going to get triangle. Okay, part B, you're going to have to visualize because I'm not going to draw it. So this plane that's intersecting is parallel to the bases, okay, to the top and the bottom. And the bases are 1, 2, 3, 4, 5, 6. They're hexagons with a hexagon hole inside. So what shape is it going to be? It's going to be exactly like the top that's cut off. So this is a hexagon. Hexagon with a hexagon hole in the center. Oops. So it's a hexagon with a hexagon hole in the center. Part C, a little hard to visualize. So if we're cutting down this cone, what shape are we going to get of the cone? We're going to get, so from here back is going to be,
no, it's going to be is not a back.
Computer stop. It's going to be a triangle. Hard to draw. Okay, hopefully you can visualize the triangle that's going to be cut. When you take Algebra 2 and Trig and Precalculus, you're going to talk about these cross sections of cones. They're going to be called conic sections. And you're going to talk about parabolas. You're going to talk about circles, ellipses, and hyperbolas. And all of those are formed by doing cross sections of cones. That's why they're called conic sections. Part D, here we have a cylinder. We're connecting, or we're cutting out here. And that is a rectangle. All right, example 5. Draw a plane intersecting a cube to get the cross section indicated. So, part A. Draw my cube. Now there's many different ways that we can do this. I'm going to do it on the left side here. I'm intersecting the 3 edges of a corner. Connect. And that's going to be the triangle, or you can do it in the front here. And I find it helps if you shade. You don't have to do both, I just wanted to show you both. B, we want to do a trapezoid here. So again, we have our cube. So to do a trapezoid, we want to intersect narrow at the top and wider at the base, or vice versa. Connect, 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 connect. Now this is, I'm going to show it to you in a better way. I'm going to start this one over. I'm going to show you front to back. Hopefully you'll see it better. So if we do narrow, wide. And there's our cross section. That's a trapezoid. Okay. Part C, parallelogram. So let's see, I'll go front to back again. Make it a little bit easier to see it. This time I want to keep these the same width. This time. Now it happens to be a rectangle, but that's okay. A rectangle is still a parallelogram. D, pentagon. Now we're getting a little bit harder now. These next two are definitely harder. I'm going to draw the cube a little bit bigger. And I did point, 1, 2, 3, 4, 5. Oop. Shade. That's pentagon. So the key is marking off where you want these to intersect the edges so that you get that shape. And the last one, part E. Almost the same as the pentagon, only instead of having it intersect at the corner or anywhere on the edge, I could have had it intersect anywhere on that back edge. I'm going to put 2 points here and here. Then 2 points here and here. Here and here. Connect. And there is the hexagon cutting through the cube. That's example 5. Example 6. It's a probability. Mark made a structure using 27 wooden cubes. So there are 9 on the top, 9 in the middle, 9 on the bottom. 3 rows, 3 columns. He painted 4 of the faces blue, so front left, front right, back left are blue. Top and bottom are unpainted. They're just wood. Then he took the structure apart, places all the smaller individual cubes into a bag. Okay? And then Leah closes her eyes, reaches into the bag, pulls out a cube. What's the probability that the cube has no paint on it? Wasn't painted at all. Well, this is one of those cubes that this face was not painted, nor were any of the faces of the little cube that are inside of this block. They weren't painted. In fact, none of the ones in this column, this one, the one below it, and the one on the bottom, that go right through the center of the big cube, are unpainted. So that's 3 out of the 27 cubes, or 1/9. So what's the probability of her picking out an unpainted cube? 1/9, 1 out of 9. What's the probability that 2 of the faces are blue? Well, which ones have 2 faces that are blue? This has 1 face that's blue. This has 2 faces that are blue. 2, 2. All these corners, there are 4 corners, 3 blocks in each of the 4 corners, so 12 total. 12 out of 27, reduced by 3, 4/9. So what's the probability of picking out a cube that has 2 faces that are painted? 4 out of 9, or 4/9. What's the probability that only one of the faces are blue? Let's count them. That has only one face that's blue. 1, 1, 1, 1, 1. There are 4 columns of 3 each. There are, again, 12 out of the 27, or again, 4/9. Now, this should make sense because 1/9 plus 4/9 plus 9/9 is, 1/9 plus 4/9 plus 4/9 is 9/9, or 1, and the probability of picking out any block is 100%. You're going to pick out a block that has either 2, 1, or no faces painted, 0, 1, or 2 faces painted. There's a 100% chance of pulling those out, so each of these individual had to add up to 100%. That's example 6. Thank you very much. Bye.